let's continue. 9 a.m. And so today, you remember a few classes ago, we introduced properties of conductors in the electrostatic equilibrium, right? So you remember something like this. So if you have a charged conductor, it has excess charge. That excess charge can be only on exterior surface, right? We've proved that, discussed that. Then electric field inside of the conductor must be zero. Electrons will keep running and running and running until, and they will never stop until they reaches these conditions when electric field inside is zero. Then electric field outside is perpendicular to the surface of a conductor. Now, since we just finished introducing the electric potential, now of course a reasonable question: what about the electric potential inside of the conductor, right? So now we need to add an additional property, and we derived it in our lecture, right? I'm not going to do it. Electric potential inside of the conductor is constant. In this case, since conductor is positively charged, of course that constant is going to be positive, right? Electric potential is zero when the conductor is not charged. Okay, so now I can add that V electric potential is, constant. I almost started writing zero, no, constant, right? Okay, I can write that a conductor in electrostatic E/static equilibrium is at the same potential, right? Okay, so we will need this. Today, right? And so now, in order to prepare ourselves for the next problem, which is 2649, we need to discuss. Okay, actually, I want to plot everything that we can. Okay, I want to plot electric field inside and outside of the solid charged piece of metal sphere, right? And also electric potential. I want to plot how electric potential changes with distance. Again, potential created by a charged solid metal sphere, right? Okay, so let me do that. Again, it's just in order to prepare ourselves for the next problem. Right. So which way? Okay, let me write. Solid charged metal sphere. So I will put a small bullet and write. So solid charged metal sphere. Right. Okay, so now what I want, as I said, I want to plot electric field and the electric potential. And we're going to assume that it's maybe, let's say, positively charged, right? So let's say this is our sphere of radius r, right? And of course, if it has charge, of course, the charge will be on the surface, right? Okay, and now let me plot electric field first. So that's electric field and versus r, right? R, it's a distance from the center, right? Okay, this is, let's say, r capital, that's the surface, right? Okay, and let's plot electric field. Inside of the conductor, what can we say about the electric field inside of the conductor? Of course, it's zero. Electric field inside of the conductor is zero. So I can plot a straight line like this. Then, outside of the conductor, we've derived it several times, even for more complicated system. You remember we had some metal sphere, there was a hole inside, and there was a point charge inside, right? So we can easily get electric field outside of the conductor by applying just Gauss's law, right? we've done. It's now it's for you. It shouldn't be a problem at all. So outside, the electric field will behave like this. Right? It decays as okay. Maybe I will write just an expression. So in this case, I can write that E equals to K Q over R squared. Again, you can easily get it, derive it using Gauss's law. And look, it looks like a electric field of a point charge position at the center. Okay, looks like E of a point charge. Right. Okay, so that's about the electric field. Now, about what about the electric potential versus R? I remember when I was taking exams to be accepted to the university, right? I remember I was asked questions like this, right? So again, this is R, right? And now let's plot electric potential. So what can we say first inside? So what do we know about the electric potential inside of the conductor? We just introduce a new property. Electric potential is constant. And since it's positively charged, so that constant must be positive. Okay, so I can plot it over here, right? So there will be some constant, right, up to R. And what about outside? Okay, that is new. Of course, we did not derive that. Right. At some point, several years ago, I did decide to derive it. It takes like maybe 5-7 minutes, kind of lengthy, a little bit lengthy derivation. So after one time, I decided not to. Of course, how can you derive it? You can just grab this expression for the electric field. And then in the previous lectures, we introduced that bridge, how to get electric potential from the electric field, that integral. Integrate it, and of course, you will get this expression. But it's, as I said, it's a little bit lengthy, right? So I decided not to do it. But anyway, you should be able even to guess what will be the dependence of the electric potential with R. Since electric field looks like an electric field created by a point charge, electric potential also should look like a electric potential created by a point charge. And of course, we all know the potential created by a point charge. It's a K Q divided by R. So we can use it, right? We can recycle that. So it will be something like this, right? And so I can write so it's, oh, not E, it's V, sorry, force of habit. So V equals K Q divided by R. And again, like V of a point charge. Okay, we will need this in the problem, which we're going to solve after this. Okay, so then we can also write now the expression for this constant, can we? Since this horizontal line and this line, they met here, they meet here, right? So of course we can also write the value of that constant. It's just when r small equals to r capital. So it will be k q over r capital, right? So over here I can write, so it will be v equals r k q over r capital. Okay, all of this we will need in a second. That makes sense since these two lines intersect over there. So of course, that's the value of the constant. Okay, so after this, we are ready to start discussing problem. And this problem will be also is in your homework, not will be, is already in your homework. And probably I will start here. Maybe I'll move to that side. Yeah, let me move to this side. 2649. So it's a chapter 26. Problem 49. Right. So this situation, we have two metal spheres. I don't have two metal spheres, I have only one, right? Solid metal spheres and tennis ball. Imagine it's a metal, right? Okay, so first, initial conditions, initial situation. This small metal sphere is charged. Charge is given. This is empty, doesn't have charge. So initial situation. Then we'll grab a long piece of wire and connect these two spheres. Of course, some charge will flow from this small sphere to this big one. We need to answer the question, how much charge will flow, and of course, how much charge will be left in this small sphere, and how much charge will acquire this big sphere. So that's the problem. Radii are given, charge Q1 is given initial, right? And we need to solve problem like this. I like this problem, and you will see why, because there are plenty of physics to discuss. It's not just grab the formula, shove the numbers, right? Get the number. It's kind of boring. um, so let me draw the picture first. So let me write. So we have two metal spheres. That's what is given. And of course, what is given? R1, R2, then Q1 is given, and Q2 equals 0. And then Q2 equals 0. So that's what is given. Okay, and so let me draw the picture over here underneath. All right. I want to leave some space above because I'm planning to write something up there. Right, so let's say this is, oh my God. Okay, the big one, I will use this. And for the small one, okay, I will do my best. Okay, looks good. Right. So this is the small one with radius R1. This radius R2, right? And of course, at some point, they will be connected with a long wire. Long wire. And let me write what is given before and what will be after, right? So let me write, so Q1, that's initial charge, right? And then what else I can write over here? Probably Q2, that's initial in the second sphere, equals to 0. Then, of course, we will have to find the amount of charge after when we connect these two spheres. Let me label that charge as Q1 prime, that's final charge. That's basically what we need to find. Of course, the same will be over here. Q2 prime, that's the final. Again, that's the question mark, right? And then, of course, I will write over there something and over there something, right? Actually, you know what? Can we also write electric potential inside of this sphere and inside of that sphere before they were connected? That's why I started with this, because we knew that, right? So V equals K Q over R, where R is the radius of the sphere. So I can write initial potential immediately, right? So V1, it's a K, Q1 over R1, it's given, right? And of course, this will be V2 equals to 0. I can write it, right? Of course, I can write expression, but since charge is 0, it will be 0. Okay, so now let's start discussing. And then, of course, I will continue writing. So when we connect them, Of course, some number of electrons or amount of electrons, of course, will travel to that sphere. How much or how many? 100, thousands, all of them. Usually, again, during the normal semesters, I bug students, right? And most of the time, the most popular answer is half of them. It's possible, but only under certain conditions, right? If you have almost identical spheres, right? But of course, in general situation, it's not the case. And of course, you realize that, of course, I'm not asking about the number of, I want to say number of students, number of charges, right? Number of electrons. Of course, I'm asking about what is the stopping mechanism? Which conditions must be met so that at that moment electrons will stop traveling from this sphere to that sphere? Which piece of physics is going to stop electrons from traveling? Stopping mechanism. And okay, this is a point where students usually, a few answered, right? I remember in the past. Let me start with opposite situation in order to get to, in order to explain our. So let's assume that we have an electron, right? Maybe I will write it here. Let's say we have an electron, right? And let's assume opposite situation, we want to move it. So what do we have to apply? Or what do we have to apply in order to force this electron to move? Like any other object, if you want to move something, you need to push it, pull it, drag it, kick it, whatever, right? So you need to apply a force. In this case, of course, it's an electric force because we're talking about electrical object, right? Of course, there must be some force. Let's assume we want to push it this way. Electric force, right? And in order to get that electric force, of course, what do we have to apply? Electric field, for example, right? It's one way of course, I can say electrical aura, but of course we can describe that electrical aura either using the electric field. So in this case, electric field must be applied in order to get that force, of course, in the opposite direction because electron is a negatively charged object. Or a different way of describing this, potential difference, right? So either electric field non-zero, right, which is not zero, and or electric potential, which is also not zero. In that case, of course, with the proper sort of delta V positive or negative, it depends on the direction. So that's what we have to apply in order to force electron to move. But in our case, we want to have opposite situation. What do we have to do in order to stop electrons from traveling? It's either electric field equals zero or potential difference equals zero. What is potential difference? It's between this and that. So pretty much at the moment when electrons stop traveling, potential over here and potential over there must be the same. So that's the condition. Of course, what about electric field equals zero? Yeah, at that moment also electric field will be zero, but this condition, electric field equals zero, doesn't give us an equation. It's just zero equals zero. What a big deal, right? No, it's not a big deal. It's a big deal. It's important, right? But it doesn't give us an equation. But the potential, yes, we have an expression for the electric potential on that sphere, this sphere, so we will be able to write the equation, right? Okay, so now let me write what we just discussed, which way I wrote. Okay, electron stops running when either electric field equals zero, but as I said, it doesn't give us an equation, but it does not give us, not use us as an equation, and I will put a big sad face. But the second, okay, maybe I will write 1 and 2, delta V equals 0. And of course, it will give us an equation, so I will put a happy face, right? Which is basically what? The potential on the first sphere after we connect them. So, and we use prime in order to denote quantities after connection. So V1 prime must be equal to V2 prime. And now let me write the value of the electric expression for the electric potential over there in that sort of like a table. I want to just write everything about the system. Okay, so this will be V1 prime. Of course, it will be K Q1 prime over R1. And of course, Q1 prime, it's unknown. Of course, I can write similar over here. So it will be V2 prime equals to K Q2 prime over R2. And of course, I can also write the electric field equals 0, right? But again, it doesn't give us anything, right? And here I can write E2 prime equals 0, E1 prime equals 0. Okay, let me separate this two columns. Right. Okay, so now so we have an expression for V1 prime and V2 prime, and we're getting the first equation, right? So we're getting K Q1 prime over R1 equals to K Q2 prime over R2. So that is in equation number 1. Let me frame it for now. And also, I still want to discuss, look, in sort of conceptually, what happens? So first, initial situation when they are not connected. So this piece of metal, of course, it's isolated. It's in electrostatic equilibrium. So electrons get settled, electric field inside 0, electric potential is constant, electrons, as I said, get settled and live happily ever after, right? Okay, up to this moment, right? So these also isolated and also in the same in the similar conditions in the electrostatic equilibrium. So electrons are happy, no one is moving, right? Electric field 0, electric potential is constant. But now once we connect them with the wire, so now what happens? We have this solid piece of metal. Piece of wire for electrons is also solid piece of metal. And they're rigidly connected. Then this sphere also rigidly connected, maybe soldered with a piece of wire. So now for electrons, this sphere, and the wire, it's just one gigantic piece of metal. A huge piece of metal. And now this big piece of metal is no longer in the electrostatic equilibrium. When they were isolated, yeah, they were in the electrostatic equilibrium. But now they're no longer in the electrostatic equilibrium. We disturb the system. And of course, now electrons will have to wake up. Oh my God, now we have to do our job again. We have to start running again in order to achieve what? The same. Make electric field inside of this new big conductor. Electric field must be 0. And of course, new potential must be constant. And of course, you will have to wait for maybe microsecond or maybe nanosecond until electrons will run properly, get the new places, and either electric field 0 or the potential difference equals 0, or the electric potential is the same on both spheres, because now it's just one big solid piece of metal. Okay, so now back to the equation. How many unknowns? Of course, K can be cancelled, right? R1 and R2 are given. Q1 prime, Q2 prime, 2 unknowns. Of course, I'm supposed to draw another big set face, because it means that we cannot solve the problem. Not enough equations. We have one equation, 2 unknowns. It means what? It means we need to search for a new equation, for a second equation. And of course, it must be outside of this electric field and electric potential, because we already extracted all possible information about these quantities. What else can be used? We need to come up with a second equation. And this part usually, so far, I don't remember a single student would give me the hint. So what can be used, what else can be used in order to get the second equation? The explanation is very simple. Imagine like you have 2 rooms. Of course, they're connected with a corridor. And let's assume that these 2 rooms isolated from the rest of the world. So, and let's assume first there were 10 people in one room. And then let's say after some time, 3 people went to the second room. what can we say about the total number of people? It stays the same, right? Which law I'm talking about? Okay, not conservation of people, conservation of charge, right? In this case, right? Because first we had, I don't know, let's say 10 electrons here, then let's say 3 electrons move to that way, I mean to that sphere. But of course, since all these electrons are trapped like those people in those two rooms, they're trapped, they cannot escape, they cannot get out. So of course, total number of people in first room plus the second room must be constant, right? So in this case, the same. So the total number of charge in both of these spheres must be constant. Conservation of charge in these two spheres, I mean in this system, right? So that's what we have to apply. This second, another fundamental law, conservation of charge. Right. Okay, so that is going to give us the second equation, right? So now let me put, and then we need to use conservation of charge, right? Okay, so I can write that Q1 plus Q2, that's the total amount of charge before we connected these two spheres, and then it must be equal to Q1 prime plus Q2 prime. So that's the second equation, right? Equation number 2. So now we have two equations, two unknowns. Physics is over. Now it's just algebra. What can be easier than solving a system of two algebraic linear equations, right? Okay, so I need to frame it, right? Okay, and now the rest is just algebra. Of course, k can be cancelled over there. So let me get q2. Yeah, let me dump also this q2 is 0. Right? We can simplify. Initial amount of charge in the second sphere is 0, so we can dump it. Okay, so let me get from here q2. Okay, this happy face is on my way, right? I don't want it. Right. So q2 prime will be equal to what? Q1 prime goes to that side. It will be q1 minus q1 prime. Again, physics is over at this point. Now it's just algebra, and you can solve this system of two equations anywhere you want, right? I'm just getting q2 prime from this equation and plug it in. I'm going to plug it into the equation number 1. Right. Okay, so this q2 prime, of course, will go into this equation, right? So now let me rewrite equation number 1. It's a 1. So k goes. Okay, let me first rewrite. K goes q1 prime times r2 equals to q2 prime times r1. q2 prime times r1. Right, so this r2 went to the numerator, and this r1 went to that numerator. Okay, and now, yeah, let me take this q2 prime and plug it into this. So as a result, we'll get q1 prime times r2 equals to q1 minus q1 prime times r1. Okay, so now we just need to combine this with that, because that's where unknown. Now we have only one unknown, q1 prime, right? So it will be q1 prime. It will move to that side. It will be moved to that side with plus. Here it's with minus. Go to this side. It goes to that side with plus. So it will be r1 plus r2 and equals to q1 times r1. So q1 times r1 is left on the right hand side. Okay, so now we can easily get q1 prime. So q1 prime will be equal to ratio of r1 divided by r1 plus r2 n times q1. That's the amount of charge which will be left in the first sphere which was originally charged. And of course it will be smaller than q1 because this ratio is less than 1. r1, of course, less than r1 plus r2. Right. And of course now you can plug it into this q Yeah, Q1 prime, and you can get Q2 prime easily. I'm not going to do it. I will just write down the answer for Q2 prime. It will be the same, but instead of R1 upstairs, you're going to have R2. Right. So it will be R2 divided by R1 plus R2 and times the initial charge in the first sphere, right? So that's the second. Oh my God. Fire alarm in my apartment complex. Okay, I will pretend that I don't hear it. Okay, sorry guys, can you hear it? Can
Just
you
a
hear
little
it?
bit.
Just okay, so you can live with that, right?
Yeah.
Okay, if I start burning, right, then I will start running away. It's a, if it's just the first floor, so it should be fine. Right?
Yeah, hopefully it's just like a test or something.
Yeah, it happens occasionally, right? Okay, so that's for 49, right? Completely unexpected, right?
I
Again,
can't hear you anymore.
Huh?
Oh, wow. I think it's my computer. My whole camera just like broke.
Yeah,
I'm
can
just gonna
hear
rejoin
you.
the
I
meeting.
still hear you.
Yeah, I think it's you, Dan.
So everything is good?
Yeah.
Okay, cool. So it's just yours system. Right. It got scared of the fire alarm. All right. So yeah, that will be also in your homework. So next. Oh, you're back. Cool. Next, we started. Okay, so at this point, we can say that we are done introducing the foundation of electric world. Okay, it stopped, right? Foundation of the electric world. All right, so from this point, now we have to start applying that foundation for some particular problems. And of course, we will start moving towards simple circuits. From this point, for quite some time, I'm not going to say, let's introduce a new fundamental equation. No, we already introduced enough fundamental equations, right? Only when we get to magnetism. Okay, it shows me that connection is not great, right? Internet connection, right? But so far you are not you're not complaining, right?
Your screen is currently frozen.
Yeah, that's what I was afraid because when alarm stopped sounding, the message appeared on my computer that not a good internet connection.
I think it was just my computer because I restarted Microsoft Teams and now I can hear you fine.
And what about the image picture? Is it
It's
good?
back now.
It's back.
Yeah, it's
Okay,
good.
so the internet got restored. Okay, awesome, great. It's outside of what I can do, right? So yeah, so now we start moving slowly towards simple circuits, and of course we need to start introducing simple elements. Like we already introduced battery in the lecture. Now it's time to introduce capacitors, then resistors, then idea of current, then something else I forgot already. Right. So slowly, let's start moving towards simple circuits. And today we first need to quickly review the idea of capacitance and solve one problem. Yeah, we should be able. All right. Yeah, I don't need this. Yeah, I can erase it. Oh. So, capacitance. So let me write capacitance. Right. Okay, so let's assume that we have two pieces of conductors, which we can call electrodes, right? And one is, let's say this one is what? Positively charged, let's say, plus Q, and that is negatively charged. All the time, if you're talking about a conductor over a capacitor, all right, one charge is positively charged, the second one is negatively charged, and their absolute values are the same. Or you can say if you add this charge to that charge, you will end up with zero. Why? Because how do we usually charge a capacitor? Of course, it's connected to the circuit, and through the circuit, electrons will just move from this electrode to that electrode, making this positively charged, and that will be, of course, negatively charged. Every time the amount of charge is the same in the absolute value. Right? Of course, then there will be some potential difference. We're going to call it delta WC. C stands for capacitance, right? And so now, if you start playing with this charge in the potential difference, you will be surprised to notice that if you start increasing charge, potential difference, of course, will go also up. But if you look at the ratio charge versus the potential difference, it will be exactly the same number. It doesn't matter how much charge you dump into the capacitor. Of course, assuming that you're dumping a reasonable amount of charge, right? Because you can damage anything, right, in the world, right? So if we assume that you dump reasonable amount of charge, ratio of charge versus potential difference is constant. It means that it's some kind of intrinsic property of this system. So we give it a cool name, capacitance. So capacitance by definition is C, 3 lines by definition basically. It's a charge divided by the potential difference between the electrodes. Charge, it's just absolute value of one of these charges, this or that, right? So don't try to add or subtract, no, nothing like this. Just think of charge of a positive plate, positive electrode. Right, so that's the amount of charge. I mean, that's the capacitance by definition, right? Then, since capacitance is used a lot, of course, it makes sense to give a special unit for capacitance, right? So, units of capacitance, farad, right? And 1 farad, it's just whatever you see in the formula, coulombs divided by volts. Coulombs divided by volts. Right, and 1 farad is a gigantic capacitance. I think the Earth has a few farads of capacitance, right? So that's why every time our capacitance is what the value of like microfarads, nanofarads, picofarads, and so on, right? So then, this capacitance, the definition of capacitance, can be applied to find capacitance of any object. And actually, any object has some amount of capacitance, right? Even if you just take a regular piece of wire, right? If you take regular piece of wire, it will have some amount of capacitance. Any object has some amount of capacitance, right? But of course, we're going to use in this course a parallel plate capacitor. So if you apply it for a PP capacitor, you will end up with the formula. I'm not going to derive it. It's quite simple. Maybe we will discuss it in the lecture, although tomorrow is the exam, not the lecture. Right? I will think about that. So let me write. So if we apply this for a parallel plate capacitor, we will end up with this formula. C equals epsilon naught A. Okay, maybe you know what? Let me draw it, because it's important to show what quantities which are involved. Let's say this is our parallel plate capacitor, right? This is negatively charged. This is positively charged, right? Of course, there will be some electric field, right? And then area of the plates, let's assume it's A. Spacing between the plates is D, right? And of course, between the plates is vacuum. So capacitance of a parallel plate capacitor epsilon naught times area of the plate divided by the spacing between the plates. So again, it can be derived from here. Let me frame it. And what's the major feature of that formula, of this formula? The major feature is, look, does it depend on the electric field? Nothing. Does it depend on the potential or potential difference? Again, it's not there. Does it depend on charge? Nothing. So pretty much it doesn't depend on a single electric parameter. It depends only on what? Epsilon naught. It's that universal parameter which basically gives us information about the electric properties of a vacuum. Basically, it tells us that between the plates we have vacuum. If it was filled with some dielectric material, we would have to write a different constant which would describe that particular dielectric material, electrical properties of that material. So it just tells us what is between the plate. Then A, area, geometry. D, spacing between the plates, geometry. So it depends only on the material and geometry. So that's why if you build a capacitor in your garage, in your basement, I don't know, you can label it immediately, because it doesn't matter how much of charge you dump or what's the potential difference. Of course, we're talking about a reasonable amount of charge and a reasonable amount of potential difference, so that you wouldn't destroy your capacitor. All right, so it depends only on geometry, right? Depends only on a geometry, right? Okay, that's the major feature of this. And similar, we will see when we get to resistors and then inductors. There are lots of similarities between these three elements: capacitor, resistor, inductor. Lots of similarities. I will keep reminding about that as we move on. Right. Okay, so that's what we need. And so whenever you work with a capacitor, every time you will have to analyze these three parameters: C, Q, delta V. Every time you will have to look. So what happens with charge? What happens with potential difference? What happens with capacitance? Every time we will have to talk about these three parameters. And so now let's look at the problem. And the problem is 54. Okay, I will continue here. So it's a 2654. Something similar will be in your homework, right? So we have a parallel plate capacitor. Okay, P capacitor. All right. So what area is? Okay, probably I need to move here. 2 centimeters by 2 centimeters. Then spacing between the plates. Of course, at some point you will have to convert 2 meters. Then spacing is 1 millimeter. Again, you will have to convert 2 meters at some point. Right? And it is connected to a battery. Battery potential difference across the battery is 9 volts. So we have basically a 9-volt battery. And in part A, first in part, actually, yeah, you know what? Let me erase this, okay? You will see in a second why. In part A, and let me label it as D1, 1 millimeter, okay? Because there will be part B, and we will change D. Okay, so now let me draw. So let's say this is my capacitor, right? Which is connected to a, let's say this is minus, this is plus, connected to a battery. Of course, you remember how to denote a battery. Just 2 bars of different length. The smaller one represents a negative electrode, the bigger one positive electrode, right? So this is minus, this is plus. And that's our parallel plate capacitor, right? So, and now the distance between the plates is D1. Area is A, right? Okay, so we need to answer this question. So we need to find charge, I think, yeah, charge, yeah, and the potential difference. So in this part, in part A, we need to find charge, Q1, and, okay, maybe let me put in the question mark first, and potential difference. Okay, capacitor, again, we will have to discuss each of these parameters, CQ, delta V. For this problem, I want to start discussing with delta V. So what's the potential difference across the capacitor? Of course, everyone who is here, right, can tell that potential difference will be equal to the potential difference across the battery. It's a kind of obvious, but let me justify it. Right? Let me justify it. Look, okay, so this is the 9-volt battery. So of course, this electrode is at plus 4.5 volts, and this electrode of the battery is at minus 4.5 volts, right? Okay, and you see this circuit kind of can be divided into two parts. This left side, you see, here there is a gap, here's the gap, so there's a left side, and here there is a right side of this circuit. Okay, let me look at this right side of this circuit. Okay, let's start with the electrode of the battery. It's a piece of metal, maybe zinc or carbon, whatever, right? But it's a piece of metal. And all right, when the capacitor is charged, so the whole system, these metals, because it's made of metal, is in electrostatic equilibrium. And of course, we know that, okay, I erased just now, but you remember, right? Electric potential inside of the conductor in the electrostatic equilibrium is constant. So pretty much any point on this electrode is at the same potential, plus 4.5 volts. Then this electrode is connected to the piece of wire, soldered. Basically now this electrode with a piece of wire for electrons is just a gigantic piece of metal conductor. And of course it must be in the electrostatic equilibrium. It's like over there we discussed. Of course, so it means that any point in this piece of wire, any point must be at 4.5 volts. Then, of course, this electrode is also soldered to the wire. So now for electrons, this electrode, this piece of wire, and this electrode of the capacitor, for the electrons is just one gigantic piece of a conductor in the electrostatic equilibrium. And of course, potential will be exactly the same. So over here, potential of all these points on the electrode of the capacitor, potential is plus 4.5 volts. Then I can run exactly the same analysis for the left-hand side. Minus 4.5, minus 4.5, minus 4.5. As a result, plus 4.5, minus 4.5, potential difference across a capacitor is 9 volts equals to the potential difference across a battery. All right. Okay, so using these arguments, we can write that, of course, delta V1 equals to delta V. Delta V, it's a potential across the battery, equals to 9 volts. These arguments will be extremely important for the second part of the problem. Okay, so this done, we answered the question. So 9 volts, of course, you knew it from the very beginning. Now, in order to answer charge, in order to find charge, before that, let's look at the second parameter. So we discussed delta V. Now let's look at capacitance. Let's look at the capacitance. Geometry is given. Between the plates is vacuum, so we can use the formula which we just derived. Okay, not direct, I just wrote it down, right? So C1 equals epsilon naught A1 divided, okay, A doesn't change, so we just use A divided by D1. Okay, so you will have, okay, I didn't want to write numbers, but I guess I will have to write 8.85 times to the power of minus 12. Units, forget about units for a second. Then, area. So 2 by 2 centimeters, so it's a 0.02 meters times 0.02 meters, so that's the area, and divided by the spacing, 1 millimeter, it's a 10 to the power of minus 3 meters. So if you calculate these numbers, you will end up with 3.54 times 10 to the power of what? Minus 12 farads. Okay, so geometry was given, so we could calculate capacitance. And now, of course, using the definition of capacitance, we can get charge. Charge equals C times delta V. So that's the first part. So then Q1 equals C times delta V. C1 times delta V1. Of course, delta V1 we just discussed, C we found, so if you calculate, you will end up with 31.9 times 10 to the power of minus 12 coulombs. So, okay, so that's part A. Of course, for part B, okay, let me hold for extra minute. For part B, everything stays the same except we will put rubber gloves and increase the spacing between, double the spacing between the plates. D2 will be equal to 2D1. So now d2 equals to 2 d1, double the space between the plates. The rest is the same. It's still connected to the battery. Okay, let me just discuss, right? And of course, we wouldn't be able to finish the solution, but I want to discuss conceptually. Again, you have to repeat these steps, analyzing three parameters, delta V, Q, and C. And again, let me start with delta V. So now we increase the spacing we double the spacing. What can you tell about the potential difference across the capacitor? It stays the same. It will be the same. Since capacitor is connected to the battery all the time will provide the necessary potential difference. I can give you exactly the same arguments like I did over here. I can run again this, I discuss this side, that side, and the potential difference will be exactly the same. All right? Then, what about, so next, delta V2 will be equal to delta V1. Then, capacitance. What will happen to the capacitance? Again, you remember capacitance depends on geometry. And we changed geometry. We increased the spacing between the plates. Now spacing is doubled. So of course, capacitance will be different. Capacitance will go down by a factor of 2, right? So it will be this number divided by 2. And then after that, once you know information about delta V, capacitance, we should be able to find charge in the sort of a new system, in the new capacitor with the system, with the distance d2, with the distance d2 between the plates, right? Again, every time I will keep reminding you. So whenever you play with capacitor, three parameters, C, Q, delta V. Okay, probably we will finish next class this part B, right? And then there will be similar problem with slightly different conditions, right? But again, you need to remember, so if a capacitor connected to the battery, if battery is strong enough, of course, the potential difference between the capacitor is going to be the same. It doesn't matter if you increase the spacing, reduce the spacing, potential difference will be, in this case, 9 volts, right? Okay, guys, so sorry for holding you or the extra 2 minutes, right? But I just wanted to at least conceptually discuss the second part.